Thank you all for showing up tonight. Appreciate that. My name's John Hinkle. I'm your chair here in the SMPTE chapter, taking over from Mr. Huddleston, who also showed up here tonight. Thank you very much for handing over the reins. Tonight, as we showed here, we're going to hear from Jed Deame in a moment, but first a little housekeeping as usual. Thank you to Ramona. Thank you, Ramona, for having us here. I think everybody knows Nevada County Media, but if you haven't checked it out, it's a pretty cool little facility they have here. So definitely take advantage of that. We have Cindy is our secretary treasurer here tonight. Thank you, Cindy. John is not with us tonight. Hey, Ian. Oh, I'm sorry. You snuck right in. We have John Laron. We have Ian Foster as well. Thank you all. Of course, Jed is also part of our managers, and Victor is here as well. Also snuck in. We have a full crew here tonight. Awesome. Thank you all for supporting us. I did this last meeting, I think. QR code if you want to go check out all the videos. There's a great repository on YouTube of all these videos from past years. I think it goes back to at least 24 and probably farther, right?
8 years.
8 years back. So plenty of good old meetings here to check out and see. And that's a QR code. I made a little quick shortcut URL. If you want to check those out, you can search for it and find it as well. But there's that. As far as what's going on coming up, we just had a couple of little talks about this possibility of nothing in December, or we do a social event in December. I'm open to suggestions. We'll aim for maybe a social event in second week of December, perhaps too far before holidays. So a little bit about Jed, besides the fact that I used to work for him at RGB Spectrum, and we're still friends.
I think that worked for you, wasn't it?
Oh, I don't know about that. We all worked for Bob.
Slave driver, yes.
Yeah, I was the slave driver up. You got to manage up, right? That's what they say. So here's the bio here, of course, and I'll let you guys read through this, but currently with Nextera Video. But he's had a long history of a lot of stuff for SMPTE with IPMX Committee, helping bring those to fruition. AIMS, of course, is the AIMS Alliance for the IPMX group. And then I mentioned RGB Spectrum is where I knew Jed from, but years at Barco and Teranex, Silicon Optics, and the Emmy for the video computer, which is pretty cool. Like I said, I've known you probably a decade almost now, or a little more
longer,
than that.
but
that happens. But extremely intelligent and has that mix. He was a marketing manager there too, so a mix of marketing and sales and engineering. It's been a pleasure to be able to bring you here. And now you've done some talks before about NMOS, I think, here with our local group, but it's good to have you back for that. And that's all I got to say. Start it out. Thank you, Jed.
okay, yeah, thank you, John. Thank you, everybody, for having me.
Yeah, I think the last talk I did was on IPMX. That kind of covered some of the components of NMOS as well, but we'll get into this a little more. But I thought since most of us anyway, have had a long day of work, maybe I'll try to wake everybody up with a really good joke. Unfortunately, I couldn't think of one. I do have a riddle though, so kind of an interesting little riddle. Hopefully nobody's heard it. I'll pose it in the form of a question. Has anybody taken a true 100% digital photograph? And if so, how? Any volunteers? How did you do it? It's kind of a trick question, but a true 100% digital photo. No, you can have optics, just no analog. So the obvious thing is, well, of course, I got one of these in my pocket. It's got a CMOS sensor in it, right? That's digital, right? No, it's not digital. The way a CMOS sensor works is photons hit the sensor and it generates a voltage, an analog voltage, and it goes into an A to D converter and it eventually becomes a digital signal. So it's not this. Any other guesses? That's not a photograph. Good guess though. That would count if if you want to take a picture of nature, let's say. Any old guys here that have taken pictures of nature way back? What did you use? What did you use? Film, camera. That can't be digital. Oh, well, wait a minute. What is film? Film is silver halide crystals on an emulsion. And how do they work? Well, when a photon hits them, They have one of two states, exposed or not exposed. That's it, period. It's a true digital photograph we took 50 years ago, but you can't do them anymore because nobody has film cameras. Anyway, that's my riddle for the day. Yes. So let's move on to the topic of the day, NMOS. What is it and why should I care? So here's the agenda. Any questions about that? Okay, no. Here's the real agenda. Okay, there'll be a little bit more detail than that. Okay, so yeah, so we'll just describe it for those of you that really aren't too familiar with it. Kind of go through the specs kind of in a light way. I'm not going to get into like the guts of the JSON messages or anything, but just enough to give you a feel of what all the different flavors, all the IS numbers and BCPs are. We'll talk about how it's used in broadcast. We'll talk about how it's evolved for some of the newer things like Pro AV and IPMX. And then security is always a big issue. How does NMOS handle that? And then how do we assure that all these new NMOS devices that are coming out are going to be interoperable? Well, we have testing for that. We'll talk about how that's all done. And then for those that get really excited about it, how can I actually try it myself? I'll actually give you some links and some ways to go and play with this. So no further ado, what is NMOS? Network Media Open Specification. Well, that doesn't really tell me much, but it was developed by this great organization called the Advanced Media Workflow Association that Cindy and I are proud members of, and probably a few others as well. And actually, if anybody wants to learn more and participate in the development of these specs, please join. We'd love to have some more members, love to get some more people driving the direction. We got a lot of new things coming down the pipe. But unlike a SMPTE standard, which I guess our parent organization is used to using, that sometimes can take many years and difficult to get to market fast. This was developed through the AMWA, which is more of a specification-based organization. So it doesn't have the full rigor of a SMPTE process, but we felt like this was required because 2110 had already been through that 3-4 year SMPTE process. And it was great, and people loved it. And look, I can use an IP switch instead of a really expensive SDI router. But how do I connect A to B? Well, you can type in the IP address of the stream that you want to subscribe to, or maybe you can make a custom control system. Oh no, it's like, hey guys, we got to hurry up and get something out there, a standard way to connect 2110 systems. So that's kind of how NMOS was born. We said, let's just do it as a published open specification with rigor. There'll be version numbers and there'll be peer review, but we can't wait another 3 years. Otherwise 2110 is just going to die on the vine. So that's kind of how it all came together. And so what does it do? It allows controllers and devices to interoperate across multiple vendors, multiple systems. And it does it in a plug and play manner, which is really important because we didn't want something that was going to be as hard to use as typing in IP addresses. So it's plug and play, push button simplicity to try to mimic the feel that we had in the SDI world, right? It was destination source take. If I can get that in a 2110 world, everybody wins. So that's kind of in the big picture what NMOS gives us, at least one of the flavors of NMOS. So that's kind of the segue into the next thing. Well, what is NMOS? Well, there's a lot of NMOSs. So in an effort to try to separate all the different specifications into two categories to make it a little easier to swallow, we came up with this naming system called NMOS Connect and NMOS Control. So NMOS Connect on the left is the one that most of us are familiar with, allows us to connect senders to receivers. There's a bunch of different specs. I'll go through these in a lot more detail because that's really the primary focus of this presentation. But AMWA also developed another type of specification that we're calling NMOS Control, and that's an attempt to be a universal control API for controlling features of products. So connects sources, senders to receivers. Control is the API to actually configure a device. So connection versus configuration. So I'm not going to go in really any detail on the control side, except just to mention some of the numbers. IS-12, so if you hear somebody say IS-12, that's this NMOS control part. It has a couple other specs that kind of come along with it. One of the newest ones is this BCP 008, which is a really interesting one, which is sender and receiver status. And it's presented in a really interesting like traffic light system where you can see is something, red, yellow, or green. It's good, it's 100%, or it's possible issues, but we're still on air, or it's red, we got a problem. So it's a way to filter out all the mess of all kinds of inconsistent status messages coming from different devices with different protocols. There's a really good presentation on it done by Stefan and Willem, and Cindy can send you a link to that if you want to learn all about BCP 008 and sender receiver status for large networks. There is some talk about maybe trying to roll that into the NMOS Connect, which is would be interesting because then it would be usable with a lot of the existing controllers. But right now it's part of the NMOS control. All right, so let's dig in a little more on NMOS Connect. See, I've already got to the why should I care. I'm glad I have some more slides after this, but why should I care about NMOS? Well, if you're a system integrator or you're a facility builder, you're doing provisioning, you're trying to set up all this cool 2110 equipment that you bought. It's a sea of cryptic IP addresses and ports and PTP parameters, and it's if you were to do this manually like they did in the first few facilities they built, you're not going to be loving life. It's very error prone. So we need a way to get plug and play access to a new device. What if I could just plug a device onto a network, a video device, a sender receiver, and just like a printer just magically shows up in your print panel? What if we could do that? Oh, well, okay. That's what plug and play is. Plug and play is fun. It's easy. Why not use the easy button? Why do it the hard way? So NMOS relies on a lot of the same technology as your printer does, MDNS or DNS-SD, domain name service. So it advertises itself so that a controller can go out there and go, oh, let me see who's out there. Oh, great, and present it to the user. You should also care because if you're an equipment vendor or a system integrator, any new facility is going to demand NMOS in their tenders. So we have to make sure it's fully supported. And control systems providers, the big systems like the Magnums and the Magellans, et cetera, VSMs, they all support NMOS. So if you're going to buy a control system to run a studio, it'll speak NMOS. So we need to understand what it is and either how to use it or how to get it into our products if necessary. And also the Europeans were a little more formal about it. They actually they came up with this document called Tech 3371 that it's like, these are the requirements, the minimum user requirements for IP-based media facility. And you can see in the table of contents on the left, they've got things like ISO 4, ISO 5, ISO 7, 8, LDP. We'll talk about what those are, but they're saying if you're going to build a studio in Europe or facility, the EBU is mandating that you have this in, which is a good thing. All right, so NMOS Connect, we'll first talk a little bit about how it fits into legacy broadcast applications and go through some of the different specs. We'll start a little bit with how it works. So this is kind of the big 10,000-foot view. I don't know if my cursor works here. Probably can't see my cursor. Oh, yeah, you can see my cursor. Okay, good. So kind of back up a little bit. This would be an example of a very simple studio. It's got two cameras and it's got a monitor. This monitor could be a production switcher or something more realistically, but let's say we have two devices. They're both outputting 2110. I think probably everybody here knows about 2110, but it's essentially packetized video. It's media essences wrapped in packet headers and sent to the switch. And it uses technology called multicast, because if you want to send a stream from A to B, you don't want to have to send it from A to B and then A to C and then A to D. You don't want to have to manage all these different streams. So we do that with multicast. How does multicast work? Well, it says transmitters, once you're turned on, you just blast your stream to the switch. This cloud is the switch here. And the switch will be smart enough to hold it and wait and see if anybody asks for it. And if you ask for it, it'll send you that stream. Only if you ask for it. If you don't ask, you don't get it. That way it doesn't flood the whole network. So how do you ask for it? Well, it's this technology called IGMP, Internet Group Management Protocol. So if a receiver wants to connect to a sender, it's pretty simple. He just sends this special kind of message, this TCP message. It's an IGMP request, and it says, I want this address, this multicast destination IP address and port is how we define streams in 2110. So he goes, give me this IGMP join for this stream. And the switch goes, sure, here you go, you got it. Okay, and as I mentioned, in the old days, we did it manually. We would type in the IP address and port and send a message to the switch. But NMOS is what automates all this. So, okay, now that you got the background, how does it automate it? Well, back to the plug and play. As soon as you plug in your two cameras and your monitors, they instantly detect the registry, also called the RDS, Registration Discovery Server, using this same plug and play DNS or MDNS technology, just like your printer does, like we talked about. So they'll listen and they'll go, is there any registry out there? And they go, yes, I'm a registry. Okay, good. Let me connect to you. Let me tell you a little bit about myself. I'm a camera. I'm from this vendor. I've got these capabilities. So all these senders and receivers register themselves. So now you've got this database, very simple, just a little program running on a PC. Could be a little Nook PC, could be a big control system, doesn't matter. And it's all there. So now you want to do something, you want to control it. Well, your control panel or your GUI with your XY matrix, anybody can go query that registry and say, hey, what's out there on my network? You got some 2110 devices for me? Oh, actually I do. I've got two cameras and one monitor. And if you're a button panel, you can build a smart button panel that'll actually put in the names, because that's part of what you advertise is I'm a Sony camera or a Panasonic camera. So it could show up Sony camera, Panasonic camera, and ISO monitor, pick another name. And guess what? How do you connect it? Destination source tape, just like you do in SDI. What happens behind the scenes? It's a little bit more complicated than an SDI router. You're not just sending a command to a crosspoint matrix, but it's not that much more complicated. The controller will send a message to the monitor. I need to point with my mouse, not my finger. They'll send a message to the monitor and tell this receiver, whether it's a monitor or a gateway, hey, Mr. Receiver, the user wants you to connect to the Panasonic camera. Oh, you don't know what that is? Well, let me tell you. It's this IP address, it's this IP port. And also, by the way, here's what format it's outputting. Every sender is required to publish what's called an SDP, a session description protocol file that tells you I'm 1080i, I've got 4 channels of audio, I've got ancillary, et cetera, et cetera. So the controller tells the receiver, send this IGMP join with these addresses. And by the way, this is the payload you're going to get. Because 2110 is not a self-describing stream. You can't just hook it up and guess what's there. You need to be told. So again, that's all part of the magic of NMOS. It'll tell the receiver will join. And if it's already connected to another stream, it'll do a leave of that stream and connect to the new stream. So it'll switch back and forth as if it's an SDI crosspoint. But again, the benefit is you're not limited to the size of a SDI crosspoint you could build. How big were you building back in the day at Envision, like 256 or something?
Usually 1,000 or 2,000.
For 1,000, yeah. So, which seems like a lot, but customers want more than that. They want 10,000 or 20,000. ABC just built that big Galaxy facility in New York, 8 floors of production, 10,000 sources, 20,000 sources and 10,000 destinations. And guess what? Anything can go to anything. You don't need a patch panel to fill in the voids. So that's really the nuts and bolts of how this all works. So you can sleep during the rest of it. It's just boring technical stuff. So at least now you know the basics of how it works. So let's dig in a little more. The first part, registration and discovery, more of this plug and play thing. This is an example of a controller. This one happens to be made by Matrox, called Conduct IP. It's a nice little low-cost one for people that want to experiment with it. It's kind of nice, or for small facilities. And when he powers up, he sends out these MDNS or DNS. There's 2 ways to do it. You configure it. MDNS is good for a local subnet. If you want to span subnets, you need MDNS. So I think I said that backwards. MDNS is for local. DNS-SD will span subnets. So usually DNS-SD is the one that's used. So he advertises himself, and then the devices all register. So next I want to do a connection. Well, now that I've registered and the controller knows who's there, how do I actually do a connection? What are my options? So that's what ISO 5 defines. Connection management is called an activation in NMOS. We had to come up with a different name. We should have just called it connections, but anyway, it's a cool sounding name. We do an activation. There's three ways we can do an activation. We can say, give it to me right now, give it to me in absolute time, like 12 p.m., or give it to me relative time, like 5 seconds from now. So a little more flexibility than we had in the SDI world. So that's your basic registration and connection. So how is all this accessed? I mean, we talk about APIs, we talk about sending messages. You know, what does it actually look like on the wire? Well, these are just HTTP posts and gets. So same thing your web browser does, right? So if you want to access an NMOS node, you just need to know his IP address, and then this keyword x/NMOS, and then whatever API you want to talk to. API just means what part of that device do I want to access? Do I want to talk to a sender? Do I want to look at its outputs? Do I want to look at itself, its node parameters? So you can go into a web browser and read any of these things from any NMOS device just by typing in his IP address and x-NMOS and some more things. And this is the message that the controller is going to send over the wires, just posts and gets. So what if we want to automate configuration of our system a little more? We've automated the registration and discovery. Okay, great. But let's say you've got your ABC, you've got 30,000 devices out there. Whose job is it to go and set something like the PTP Grandmaster domain on every one of those 30,000? That's a job nobody really wants. So the next thing we did in this series of specifications is ISO 9, which we call system parameters. And this allows us to have another little service out there, again, running on a little PC or in a control system, using DNSSD again, saying, I'm your system parameter server. And then any node that supports ISO 9, it's optional, you don't have to do it, but most of them do, will find this server as well. So it found his registration server, then it found this other server, and he can get all that information that's common to every system. So you don't have to put it in manually in 30,000 systems. What's the information? Things like the versions of NMOS supported, PTP domain, announce intervals, all the things you need to be able to connect to a Grandmaster, whether you're secure or not, heartbeat intervals, and syslog information. So that in one fell swoop on PowerUp gets sent to everybody. Kind of a nice little feature. Okay, the other thing, in addition to ISs, these specifications, we have BCPs, best current practice. And these BCPs are kind of little mini specs that help make things a little bit easier. This one is called natural grouping. And the idea behind that is, remember in 2110, we've got flows for every type of media. We've got a video flow. A flow is the stream of this content going across the network. So we got a video flow, an audio flow, and ancillary flow. All three presumably coming from the same source. In this case, they are. So how can I refer to those as just a single entity? And that's what this grouping does. So it's just another little keyword that you type in the setup when you're setting up a system. A controller can link these together, the audio, the video, and the ANC flow. And in the controller, you just see something like playout master, if that's the output of your production switcher or whatever else, or your playout server. Okay, other new and interesting things. As NMOS evolved and we built more and more studios out there, some challenges came back and feedback to AMWA. One was, if I put 50 Sony cameras out there, they all show up as Sony camera, Sony camera, Sony camera. Which is which? How do I find the 17th one that I think I'm having problems with? So we had another BCP for this called Asset Distinguishing Information, and it's just some basic parameters. It's manufacturer, product name, and instance name. So I can put in something like and this is, the idea is that the vendor would provide this, and the vendor would have this unique instance identifier like a serial number. So if you see a problem, you see a red light on your console, you can go see what serial number it is and then track it down and look it up. The other thing with the emergence of multifunction boxes like SMP from Imagine and other similar products that could be anything, they're programmable as to whether it's a format converter or multi-viewer or whatever, Lavo Home, those kinds of things. put in the function too, because the function will change from time to time. That should be updated. If you turn a piece of hardware from a format converter into multi-viewer, you probably want to tell NMOS that so you can tell the user that so you're not routing something that looks weird. Okay, well, what about audio? Audio is often forgotten, but we tried to give it good service in NMOS. As you may recall, in the good old SDI world, we could do audio shuffling, but it was a little bit complex. You needed embedders and de-embedders, and there was a lot of extra hardware required to and shuffling matrices. In 2110, remember, it's a separate stream. You throw your audio streams on the network and your video streams. Your receiver can grab anything he wants, right? He can grab video from one, audio from another. You could actually grab multiple audio streams and pick what channels you want from each stream. So if you're a receiver gateway, let's say a 2110 to SDI, with this audio mapping technology, ISO 8, you can now decide what channels you want from each stream. This is a little hard to read, but stream 1 on the top is channel 0 through 7. Stream 2 also has 7 channels. And along the top would be your SDI output, 16 channels of embedded audio. So you could just pick in whatever order. I happen to do a diagonal in this example, but you can mix and match audio channels. There's no extra hardware, right? You just receive an extra stream and bucks it together into your output. Life's good. Okay, what about event and tally? So let's say you got a production switcher and you want to select either your preview, your program source, or your program source in particular, and you want your tally light to go on your camera. Well, you could do it by sending a TSL message across the line. That works. That's great. And actually, absolutely nothing wrong with that. But we wanted a NMOS way to do event and tally that had a little more capability than just tally lights. So this is the way the tally system works. You have these nodes and devices like production switchers or anything that generates an event, and it sends these. So this is a good slide to actually talk about the NMOS nomenclature. It has these things called sources, which is the originator. Could be the originator in this case of a button press, or it could be the originator of a video stream or an audio stream. Then you've got flows, which is actually the stream itself. Then you've got senders, which is how we transport this media information over the network. Well, you notice there's 2 different kinds of senders here. There's a WebSocket and an MQTT. Why is that? Well, in the committees, we couldn't agree on which one it should be. There's pros and cons. So WebSocket has the advantage of it doesn't need any additional brokers in between. A WebSocket, you could connect directly from the sender to multiple receivers. But what happens if you have 50 receivers or 100 receivers? Now you're putting too much burden on the sender. So, well, we'll use MQTT. MQTT, I'll try to spell out the acronyms because there's a lot of acronyms in this world. Message queuing is the MQ part, which came from IBM. That was some original technology they had for sending messages over Ethernet, but turned out they didn't use queuing, but they still called it MQ. TT is telemetry transport, message queuing, telemetry transport. That needs a broker, so it's just a one-to-one connection from the sender to the broker, and it's the broker's job to send this to everybody else and make sure they're happy. So senders are required to send both. Receivers can pick one or the other. So in this case, you press your program button, this message comes all the way across and goes to your camera and lights up the light. Well, it's a lot more capable than TSL tally, but you can probably see why TSL is still pretty widely used today. It's a lot more complexity than a lot of people need. So in all honesty, this hasn't really reached any serious adoption yet, mostly just experimentation. But I wanted you to know about it. Okay, so that's kind of the status quo of NMOS that's out there and used in broadcast broadly. I wanted to talk a little bit about where NMOS is going and some of the new capabilities. So for the Pro AV market, they need some additional capabilities that broadcast doesn't need. So we came up with another BCP called 006 to handle compression, in particular JPEG XS. There are different BCPs for different codecs. There's a different one for H.264, 265, for instance. So what this does is specifies additional information that you must put in the SDP file and additional information that you must announce to the registry if you're a device. Because remember, we want to be plug and play. We want to make sure that a sender and a receiver can always be connected and we don't ever have a bad user experience. So we want the controller to know, hey, this sender is sending JPEG XS and this receiver can only do uncompressed. The controller is smart enough to know not to allow you to connect those. You won't even have a little box in your XY crosspoint grid. And if they have the same capabilities, it will let you connect them and you can do your thing. So it uses a bunch of the other things that I mentioned, but you kind of got the gist of what that does. Okay, so what's the other thing the Pro AV world needs that broadcast doesn't need? EDID, good old EDID, HDMI, right? They're not SDI, they're HDMI. EDID's a wonderful thing, right? You plug in your monitor to your computer and it tells your computer, hey, here's what resolutions I can do, by the way. And your GPU is smart enough to go, oh, okay, great, I'll pick the highest one, or I'll let the user change, but I'll give him a chance to change his mind if he wants. Well, wouldn't that be nice to have in the Pro AV world? If you're trying to replace HDMI cable with 2110 with the IPMX layer on top of it, you better support EDID. So what it does is it provides additional information. We talked about an endpoint can say if it's compressed or not. Well, let's just extend that a little bit. Let's extend these receiver capabilities and allow an endpoint to provide all of its supported resolutions and capabilities. So that's really what IS-11 does. The receiving device connects to the monitor. The monitor tells it what it can do, and it publishes that. Things like frame rate, frame size, color sampling, number of channels, packet time, all that stuff is in there. I do have a picture because words get boring after a while. So here's a typical system. If you wanted to connect a PC to a monitor that are HDMI on both sides, and you want to use IPMX in the middle. Again, IPMX, for those of you that missed my last presentation, it's 2110 with a couple layers on top to support things like asynchronous transport, compression, etc. So first thing that happens, you plug in your monitor and he sends an EDID to your gateway. So again, we have HDMI into a sending gateway that's converting it to IPMX, RTP, real-time transport packets, to the switch, out of the switch to a receive gateway. This guy is IPMX in, video out, HDMI video out to a monitor. So the first thing you get is the monitor tells the receiving device what his capabilities are, and this transmit gateway, he's got an HDMI connector on him too, so he's going to tell the PC what his capabilities are. But that's just standalone. They haven't really looked at the big picture yet. Nobody's done a connection. So, so what you want to do, this is a little more detail on what I just said. These receiver capabilities are now combined, the monitor's capabilities plus this gateway's box. So the monitor maybe can do 50 different resolutions, but maybe the gateway can only do 2. So you want the least common denominator. So it's the job, IS-11's job on this receiver is to find that least common denominator. So let's say these are all the things that it can do: 720p, 2160p, it can do uncompressed, it can do JPEG XS, it can do HDCP. That's the least common denominator of the gateway and the monitor. So he sends those over to this NMOS controller, which again is like a PC running some software. Could be in a big box, could be in a little box, doesn't matter. Transmitter does the same thing. He sends his capabilities over. So now the controller can present this to the user and only show legal connections. So the things I've underlined are the common ones. So is this a legal connection? Well, yes. They both support 2160, JPEG XS, and HDCP. So what happens now is the controller does another least common denominator between what the sender can do and the receiver can do, which is these 3 underlying things. Like if you send it in this mode at this resolution with this protection, we know it's going to work. So send that message over to the sender, and guess what the sender does? He makes a new EDID file to tell the PC or whatever HDMI sender is, if you send me this stream, it's guaranteed to work all the way through the end. Because that's the big thing we want to avoid. Somebody routing A to B and getting black screen. Well, what's wrong? Well, is that HDCP? Is that compressed? Is that 4K and that's HD? So a lot of stuff happening behind the scenes to make this all work. But at the end of the day, we're really just moving this EDID from the monitor all the way through the network. In the one-to-one case, you say, why do I need all this complexity? Just pass that EDID straight through. But remember, it's not one-to-one. You could route that sender to any receiver, to 10 different receivers. You don't want one to work and one not to work. You want them all to work. So the controller's job is to make sure that they're all compatible. Yes, sir. Questions?
So if you already have one link established, and then you have another monitor pulling source from that same computer that has different sets of EDID's limitations.
Yep.
And it's not going to be compatible with the existing stream. Is that going to cause it to renegotiate that EDID back to the computer?
Yeah, excellent question. So the basic scenario is, let's say if you just route, let's say you got a computer that can do 4K or HD, and you've got a monitor that can do 4K to HD. And so the controller says, yes, these will work. I can connect them together. And then the computer is going to run in its highest resolution, which is 4K in that case. If you connect another monitor that can do 4K and HD, it'll go, yeah, no problem. I know that'll work. I'll let you route it. But what if you want to connect a receiver or monitor that can only do HD? And this is kind of where you're heading out. What happens? Well, the controller will say yes. So I'll have to preface this because some people get scared when I say this. There's a special mode you can turn on in the controller. It says auto adjust resolution. Some people like, no, don't ever, I'm a broadcast environment. Don't ever change my sender resolution. That's not what I'm talking about. You can put it in that mode too, but let's say you're a university or a church or something. You just want the thing to work. You don't care if everybody gets 4K or HD. You just want all the monitors to light up. So when that last monitor, that HD monitor gets connected, it will then change the EDID back to the source, to your point, and say, hey, Mr. Source, you better send me 1080p because that's the only thing everybody can swallow.
You'll get a video interruption when that third monitor finally connects.
Yeah.
You'll see that on the other monitors.
Yeah, you'll get a little flicker on that, and that's that's something a good controller will put up a little box that says, "Warning: all existing monitors will flicker." Is that okay? Yes.
And could the sender choose to send a second stream at HD and leave the 4K monitors with 4K?
I'm not quite sure how you do that. You need another connection, right? Another HDMI connection. But so I think that in that case it would show up as a separate transmitter, and the controller would show it as a
Scaler to take 4K and scale it
down.
That's the cleaner way to do it, but it adds a little bit of cost to the system. So this was a feature that was put in to support more of the lower cost systems, house of worship, entertainment, but they just want it to work. Yeah, exactly.
Maybe send out a 4K HD version.
Yeah. Yeah. Right, exactly. So if you put out two streams, no problem. Nothing's going to flicker. The controller, because then you'll put it in a mode that says, don't change my resolution. And he'll say, stream 1 can't go to that last monitor. I'm not even going to let you connect it. But stream 2 can. And if you know you're sending the same thing on both streams, great. Connect that one and nobody flickers. So
I see that you have knock out the HDCP side of it, call it they'll call it an HDMI sender and receiver. This could also function for just 2110 even compressed, right?
Yeah, absolutely. There's no restriction that IS-11 only has to work in IPMX. Good point. And it's really anytime you're bringing an HDMI sender or receiver into a system. So if you got a 99% SDI system, but a couple HDMI devices, you want to know. You want your controller to know what you can send to those. And certainly you would turn off the mode of resolution changing, but you want it to be compatible. Yes, sir.
Are the devices pretty much passive in the exchange in an environment of an NMOS controller? Is just the NMOS controller picking the SDP file from the sender
and combining with the receiver, do the devices do anything in an NMOS controlled environment?
No, they really just, they consume the SDP file, so they know how to set up their hardware to expect the stream at a certain resolution, for instance. And then they're told to command the switch with this IGMP join message. So it's pretty transparent. There's not a lot of processing going on.
What's the latency for some of this stuff?
It depends on the implementation, but fraction of a second usually. Yeah. So, and you can do salvo commands if you want. Those go a little faster if you want to send 64 connections to a production switcher or something like that. So yeah, it's pretty quick. The systems usually run embedded Linux because you want PTP and usually running PTP4L Linux stacks and things like that. So it's not quite that, 100 nanosecond kind of hardware guy timing, but in software world, it's pretty good. It's it's milliseconds. It's not seconds. Okay, good engagement. Any further questions about NMOS for IPMX? I think that's probably the last IPMX slide. So again, additional extension. So that this, I don't have a slide for it, but a spec we just finished was for PEP, stands for Privacy Encryption Protocol. That's encrypting the streams. So you can encrypt video, audio, whatever. And it's a method kind of like HTTP, but whereas HTTP is very rigid and it says you must do it this way and you must pay for licenses and buy keys. This is more of a more broadcast friendly, or even the medical industry is very strongly interested in this. It says you can use whatever encryption you want. Usually it's AES of some flavor, but you can use whatever length you want, whatever CTR modes, etc. And it's a means of signaling what encryption you're using to the controller. Same thing as everything else we've talked about. The sender says, I'm capable of these types of encryption. The receiver says, well, I can receive these types of encryptions. Okay, let's negotiate and find something that works, set the system up, and it'll be guaranteed it can connect from A to B. So a couple extensions for that and for HTTP as well to share that information. So that's the newest along the basic connection capabilities. Since I started talking about security, what a good segue. What about security? Well, we talked about media security of the actual packets themselves. Well, what about the control security? What if I want to be able to make sure some bad actors can't go in and route something on air? The janitor in the bathroom jacks into the local internet, and I hate to say it, but if you can do an HTTP post and you can find the registration server and the controller, you can route something. So it's kind of a big problem. We need to make sure that we put a little bit of encryption on top of this. It's not an outside threat. It's not the Chinese hacking into the studio. It's going to be some disgruntled worker that's going to go in and we'll show those guys. Yeah, let's do this. So how's NMOS handled? NMOS security handles this through another set of BCPs, BCP 003. The first one, -1, just implements TLS. If you don't know what TLS means, it's transaction layer security, which is a fancy way to say HTTPS. So notice all your web browsers, you try to HTTP something now, it's like, no, I'm not gonna let you do that. You must HTTPS it. That means it's encrypted both ways. And if you end up on some website that isn't, it gives you this big warning like, danger, danger, you don't click here because it isn't protected. Well, it's telling you TLS is not enabled on whatever website you're going to. It's not necessarily you're going to get a virus, but they're just trying to force everybody down that path. So if every website does it and shopping sites do it, why don't we do it in our broadcast system? So a lot of interest around it, seeing a lot more uptake in it. And it's as simple as just adding that layer of security on all these NMOS packets that are going back and forth. And it's also something that's advertised in the registry. So the controller is smart enough to know, you've got a secure node. I'm going to speak to you with HTTPS, but you've got a legacy node. I'll speak to you in regular HTTP. So it's fully upward compatible. 0302 is authorization, which allows you to decide which individuals might have permissions to do certain things. And then 03 is the certificate provisioning, because anytime you do encryption, you have to handle the certificate so that you know who's authorized and authenticated to do what. So there's authentication and there's authorization. They sound a lot alike, but they're very different. Authentication means I am allowed to do something in the system. I've logged in, you've accepted my password, but maybe I'm not authorized to do anything other than look at a log file. If you want to be authorized to do something like a route, you need this IS-10, which is the authorization thing. It uses a bunch of fancy internet technology like JWTs, JSON Web Tokens, OAuth, which is an authorization system, which is really just a way to ask someone for a username and password and have a database that says what he or she is authorized to do. So it's not super crazy technology. So time for more pictures. Show me a block diagram of how this all works. Okay, I know, Jed, you've told me about sources and destinations and controllers. We understand that so far. How would I do a secure connection between a source and a destination from my controller? Well, the first thing, I'm going to add a new device that wasn't there before called the authorization server. Again, another PC or a process running on a PC in your controller somewhere. And then my broadcast controller, instead of just doing this activation, telling the sender to send and telling the receiver to join, he's going to send a request to the authorization server. And he's going to send the user's credentials. And he sends this as what they call an OAuth authorization request. The authorization server will go, okay, yeah, I know who that is. His password makes sense. I'm going to send back this token, this JSON Web Token. Now the controller can send this token over to the source along with the activation, say, all right, turn on your stream. Here's the token. Well, how does the source know that that's a valid token? Well, he checks that against the public key of the authorization server, and using this PKS encryption, which is a whole nother presentation, but very clever way where you can share keys and not actually have to send a key in the clear and be able to detect to have the same key on both sides. So the source authenticates it, the JWT against the public key. He starts sending his flow, but the destination still has to subscribe to it, right? He still has to do that IGMP join. So he's told to do that by the controller, also with another JWT token. He authorizes it against the same public key, and then he does that join and the stream flows. So a little bit more working under the covers, but it still builds upon the same basic technology that we've talked about. Okay, well, we talked a little bit about the technology. Well, how is all this tested? How do I know if I buy an NMOS product that it's going to be interoperable, that it's implemented all this stuff right? Well, AMWA has developed a very comprehensive set of testing routines. They're actually Python scripts, and here's the link to them. If you want, you'll see it in when the publication, when it's published. But you can download this test tool, and this thing in the upper left is what you get. It'll ask you which test do you want to run. You want to run them all, you want to run one or another. And then it gives you these nice results in a nice tabular form. Green means passed, red means failed, etc. And then this eye chart over here is a little hard to see, but it shows all the different details of the test. Some of them are for nodes, some of them are for registries, some of them are controllers. So it's a variety of tests to test all the different pieces in your system. So now I'm sure all you were saying like, wow, this is awesome. How can I try this? I always wanted to try NMOS myself. How do I do it? Well, actually, you can download a free program from Riedel. Our friends at Riedel have something called NMOS Explorer. And if you download that and you download the Sony registry, which is also free, you can plug in a couple NMOS devices, and guess what? They'll all pop up right here. Because what this program does, Riedel NMOS Explorer, he goes and looks at that registry and just presents it in a nice graphical way. Here's all my nodes, which are my hardware boxes. Here's all my devices, which could be two different things in the same box. In this case, they're the same. And my senders and receivers. And well, I want to connect a sender to a receiver. Well, you just click on one of these senders and drag it over and drop it on a receiver. Boom. You've done your first NMOS activation, all for free. You just need to find a couple of devices that are NMOS capable. If I want something a little more complicated, you can get, a little more capable and slightly more complicated. You can get a full-on NMOS controller like the one from Matrox. And this might look familiar to anyone that's used an SDI router. You've got senders along the top and receivers on the left, and you just click the box for that cross-point connection you want to make. And in one click, boom, you've made that connection. You don't even have to drag and drop. And notice there's a lot of blanks here. Anybody remember why there might be blanks here? Anybody paying attention? Not compatible, exactly. So that's what the controller is telling you. It's like, hey, this is a IPMX stream. You can't connect that. You can't connect your, in this case, your AJA uncompressed transmitter is not going to connect to this IPMX compressed receiver. It's not going to work. We're not going to even let you try. So that's one of the beauties of NMOS. So you get a lot more capabilities with a program like Conduct IP. You can right click on these things and see all the parameters. You can see everything that they advertise to the registry. Okay, so takeaways, NMOS 4 and 5, which are kind of the most basic things that have been around for years. They're stable, solid, mature. They've been out there, they're well proven, and they're offered. This says most all, but it's really all new 2110 products. I haven't seen anything in the last 5 years that didn't have basic 04 or 05 capabilities in it. Control systems are greatly improved. We're doing more and more testing of controllers, which was kind of a gap that we had about 2 years ago. All the nodes were great and tested and had all these nice JT&M badges, but the controllers weren't all tested. Well, that's been fixed. So we've had rigorous testing of the controllers. So you can now feel confident going to the JT&M website, by the way, which is where all this database is stored for all the test results. And you can see here are all the nodes that have passed, and here are all the controllers that have passed. It's getting a little bit dated. We just talked about in the AMWA board meeting the other day, we need to have a way to update it. We need to have a mechanism for vendors to do self-testing. So that's something I'm heavily promoting personally, is I think that's the right way to do it instead of forcing everybody to fly to some cold part of the world, usually over in Europe, and test everything. Let's just run these automated test scripts. We've generated them. They're easy. You just double click and run. So follow the honor system. Nothing wrong with that. We're an honorable group, and people publish their results, and then they'll be put on probably both the AMWA and the JT&M websites. So stability's here. We've got a bunch of features on top of the basics, things like the audio shuffling, things like the system parameters, the grouping, and far surpassed all the capabilities we had in SDI. Security adds a whole new layer that is sorely needed in the industry. And the latest extensions for Pro AV are really going to help NMOS really spread and do great things in a lot of other places. All right, that is all I have. Thank you so much for your attention.
Question,
Yes, sir.
are there various versions of NMOS?
There are.
Somebody has to, the controller, someone say, well, you're this version, how am I gonna make you understand each other?
Yeah, excellent question. There are multiple versions. There's in the connection management, there's 1.1, 1.2, and 1.3. They were designed to be backward compatible. And the controller is smart enough to know that's one of those things you advertise as part of that plug and play process. You send a little packet that says, here's what version NMOS I'm running. Mr. Controller, don't try to send me a command that I don't understand.
Okay.
But the changes were actually very minor. They were mostly just adding in additional capabilities. So we wanted to add in additional types of support for these additional IS numbers and PCPs we're adding that didn't exist when version 1 was written. So most of it's just
Maybe as new
adding
codecs
that.
come along.
As new codecs come along, we're trying to not change the underlying connection management, the 04 and the 05, and we've done a pretty good job so far because those were anticipated. We knew there were going to be other codecs. We knew there were going to be capabilities, things like compression, things like encryption. So there are already placeholders for those. So, yep, good question. Victor, yes.
Another question. TSL, you never mentioned TSL.
Yeah.
Can you maybe explain what that is?
Okay, yeah, absolutely. So that's just the way tally is done today for the most part. There are a couple systems out there. It's just a basic IP, very, very simple. The spec is like 1 page. So that's why it's very commonly used. So if you have a production switcher and you want to light up your tally lights on your cameras, today it's the TSL protocol. NMOS has a very complicated way to do the exact same thing, but I'm just saying it's not really widely adopted.
One manager who's missing works for TS.
Ah, that's right.
So he could help
Ian
explain.
could have explained all of it. So yeah, they named the protocol after themselves and it's widely used, but has nothing to do with NMOS.
Oh, nothing to do with.
No, nothing to do with NMOS.
Just, and why, if that works so nicely, why, are vendors offering NMOS also over their, APIs?
It turns out they're not. Vendors are not offering ISO 7 capabilities because Tally already works, it's there. ISO 7 is kind of in limbo at the moment. I think Real is the only one that I know of that did an implementation, but they don't have anybody else to talk to. So it didn't really catch on. So yeah, that was the point I was trying to make. There is an NMOS replacement for TSL, but it's not being used.
What is the role that AIMS is playing in the network medium space?
Yeah, AIMS. So AIMS is the marketing organization. So there's a lot of organizations out there. Obviously, you know about SMPTE in the 2110 space. There's VSF, the Video Services Foundation, that wrote the original 2110 specs that got handed off to SMPTE. They're more of a protocol definition kind of group. And then there's AMWA, which I've talked a lot about. They developed the specifications for software control, NMOS, but there wasn't really any cohesive higher level group that was handling like more of the marketing functions and the coordination functions and liaison functions. And how do we tell the world about these great things that we're doing? So that was kind of the point of AIMS, is initially as historically, it started out as a marketing organization to try to kill anything that was non-standard video over IP, like the Evert system and the Sony.
Mike Cronk.
Yeah, that was Mike Cronk, Grass Valley. Yes, I should turn off the recording stuff. It was all good stuff because had they not done that, I mean, there were a lot of good systems out there. There's nothing wrong with Sony IP Live. There's nothing wrong with the Evert system, but they were different, and we didn't need another, VHS beta kind of problem again. So they did a really useful thing for the industry, for the end user, because they were the ones that were saying, "Don't do this to me again. I don't want beta SPs and digibetas and all this stuff competing. D5, oh my gosh." So that's kind of how it started. Let's make sure there's one and only one, and it'll be called 2110. And nobody buy anything until that stuff is passed. So since we've gotten through that, AIMS has kind of evolved more into looking at IPMX, looking at any other use cases for 2110 and NMOS, and making sure that they're used together and everybody understands the role and the benefits that they provide. So I get to sit on all these calls every week. So there's an AIMS technical working group that is kind of looking back. That's every fourth Friday, I think. It's like, what are we missing, guys? What do we need to do? Is 2110 done? That was kind of the last week's call. Is we think 2110 is done. We think we're going to like close down the working group unless somebody speaks up. We'll just do the normal annual reviews. And then there's a marketing group, AIMS marketing group, that's focused on things like, what should the criteria be to say you're IPMX? We don't want any vendor to just say, "Oh yeah, I'm IPMX." Because if you're not interoperable, guaranteed, it's not going to make it, right? That's one of the reasons Dante was so successful. If it says Dante, it's just going to work. So AIMS said, if you want to get the sticker, if you want to be able to use the IPMX logo, you must pass these tests. And there's a test event actually coming up in January, got my J's mixed up, in Geneva, where about 10 or 15 vendors are going to come and run through a rigorous test plan, and they'll get their approval to use the IPMX badge. And if you haven't been there, you don't get to use it. So AIMS is driving all of that. And then they send the requirements over to VSF and say, "Hey, VSF, this is what us marketing people have decided is the criteria for the badge. Please make a test plan for this so we can make sure it passes."
And one thing you mentioned was JTNM, Joint Task Force for Network Media, which is a group within VSF, which has come up with.
Yeah, JTNM was trying to do some of the functions that AIMS is doing now. So Joint Task Force, so it's EBU, SMPTE, AMWA, and VSF, I think are the 4 members, if I remember that correctly, of this Joint Task Force on Network Media. It was mostly administered through the EBU folks, and they're the ones that sponsored all the original testing, the Plug Fest for the 2110 devices that we did for 3-4 years. And everybody got their little JTNM certified badges. JTNM, I guess ever since Yigvin left, he was running most of these programs. They kind of really didn't participate as much.
Okay.
And they weren't really that interested in IPMX. And that was all the new stuff that was happening was IPMX. So that really drove AIMS to step in, and since their mission, their initial mission had been accomplished with full success. Well, what do we do now? Well, nobody's picking up this testing for this new IPMX stuff, so let's do that.
GTNM used to publish a 3-year roadmap. So is that not happening anymore? Not driving that?
I haven't seen an update of that roadmap in quite a while. So I think there's still some work going on, but I think it's minimal. Now that the EBU itself is pushing a lot of the new activities. So on a slight tangent, what's the next big thing in broadcast? Well, it was analog, then SDI, then HD, then 4K, then 2110. What's next? What's the big next? Anybody know? Well, it's kind of a technology. Anybody heard of dynamic media facility? Anybody hear of MXL, media exchange layer? Well, it's coming. Yeah, somebody has. So this is the dream. Like, okay, wouldn't it be nice? This is Mr. Customer, Mr. Television Studio. Wouldn't it be nice? I've got 100 boxes from 100 vendors with 100 APIs. It takes me 6 months to integrate all this stuff together and make it all work. And finally, when I get it all working, it's becoming obsolete, right? And I have to change it out in 4 years. We went from HD to 4K and maybe 4K to HDR, and I got to change out all this equipment. Wouldn't it be nice if I could just buy a rack of servers like those IT guys? Yeah, like those Google guys. I want to buy a bunch of servers and just spin up instances of whatever processing I want to do. Victor knows a little bit about this. So it's like, wouldn't it be nice? You can run a multi-viewer on a PC. Works great. Why not? Right? Why can't I do everything else in a PC? So, well, turns out you can do almost anything, but it's super inefficient for a lot of the really hard stuff. But so let's say we can do everything in a PC. How do we move something from A to B, from PCA to PCB? Well, you could encode it in 2110, send it out, use a NVIDIA card or something, a couple $1,000, Mellanox NVIDIA card, send it to the next PC, decode it, process it. Well, isn't there a better way? What if we could send it as data? What if we just send packets of data from process to process inside the PC and from PC to PC? So that's what this DMF, dynamic media facility, the idea is you buy a bunch of servers and then you buy a software license for a format converter, a software license for a multi-viewer, and you deploy it on however many servers it takes to meet that need. And eventually it'll be less and less thanks to Moore's law. And but you're not using 2110 anywhere except the very ingest from your camera or maybe your satellite receiver, and then only at the very output side, you're pushing it out. So how do we manage all these flows, all this stuff going back and forth between these software instances? Hey, how about NMOS? Right. So yeah, that's the next big effort of AMWA and the EBU. And guess what? Now there's a JTDMF, Joint Task Force on Dynamic Media Facilities. So that's kind of taken a lot of the energy that was in JTNM, and they're focused on, how do we do this in a vendor neutral way and publish open specifications. And they're actually using can't remember the repository. So they're using just regular C internet repositories to save this stuff. Open Linux Foundation, I think, is the one they're using. So the idea is that you don't have to read a spec and do your own implementation, just download the code. And if everybody uses the exact same code to talk between process A and process B, likely it's compatible. So that's the idea. So big proponents of that are Grass Valley, Lavo, Riedel, a couple others. So that's the next big thing. I think it'll take a few years before it really takes off. Yes, sir.
So they trying to do that compute and processing like with GPU cores or FPGAs or still to be determined?
Yeah, so the dream is it's CPUs, right? The non-technical, end user guy is like, why can't I just have a rack of Dell servers, right? They're PCs, they can do a lot of processing, and they can. And yes, it works, but it takes a lot of cores to do something like a high quality deinterlace, like tens of cores. So you don't really quite get the density that you got in an FPGA. So like, well, all right. Well, why don't you? Because CPUs aren't made to do that, right? They're not made to move a lot of data. Their ALUs are made to handle these big wide words, not a bunch of pixels that are maybe coming from different locations. So super inefficient. Oh, well, let's use a GPU, right? GPUs are super efficient. Well, not so much. GPUs are made for vectors in and images out. They're rendering engines. And yeah, they're getting better. They're adding some more capabilities, but they still don't have the processing ability to be able to operate on useful data every clock cycle. So that's their biggest flaw. So a GPU, if you're lucky, highly optimized, you can get maybe 20% of the tera ops that they advertise. So really, they're telling you how many tera no ops per second they can do. So the people that have tried this, that are in this space selling product with software running on CPU, when they ported it to GPU, they weren't getting the 10x they were hoping for. They got about 2x. So it's like, yeah, is it really worth the expense? So
I'm not familiar with this concept. Super interesting. Thanks for letting us know. But I can see that there's a lot of headroom. That's a lot of inefficiency if you do this only in IT. A lot of power consumption, not dense enough. But the scalability, the flexibility, that is pretty interesting, right, for customers.
yes, that's the dream. Is I have this sea of compute resource, and I can spin up, 3 of these and 5 of those and 6 of those, and I can have 4 medium-sized productions or 2 big productions or 8 little productions, all and not run out of gear because I can do whatever I want. It's just, it's about a 5 to 10x cost adder to do that today. So what's the answer? Well, I mean, you could wait 10, 15 years until Moore's law catches up. That's one answer. I have an answer. Maybe I'll do a presentation on that next year, but the teaser is, somebody mentioned FPGA. Well, if you could make an FPGA act like a CPU or GPU, and you could buy them in off-the-shelf cards and plug them into servers, and it gave you that fully flexible capability, would that be interesting? And now you're not running 1 or 2 format conversions on a server. You're maybe running tens of format conversions. Maybe that's interesting. Well, maybe somebody will invite me back next year and I'll talk about that.